Well, in my earlier lecture on the problem of falling rod on the horizontal floor, I said I'll follow up this problem to reveal some interesting insight into the problem, and so I have come back. Now, in this problem, if we recall, the rod was rotating on a rough horizontal floor, and at any instant the rod makes an angle theta with the vertical the problem that we are working from the frame of reference inertial, or we call it ground frame or lab frame. From this inertial frame, the forces that we looked into the system are gravity mg, the normal reaction n, and static force of friction Fs. Now these are the three forces acting on my system. And obviously the system has an angular velocity theta dot and angular acceleration theta double dot, d theta by dt and t2 theta by dt square respectively. The center of mass has tangential acceleration at as well as radial acceleration ar at this instant, where at is equal to L by 2 theta double dot and ar, the radial acceleration, is theta dot squared L by 2. This is the motion of the center of mass. Now, in our earlier discussions of basic mechanics, we said that a force of static friction comes into play when there is an external force trying to give the system a tendency to slip, and static force of friction comes into play to oppose that tendency. So here that static force of friction is horizontal. That means it has a tendency to slip horizontally, and that must be due to some external horizontal force. But we find no horizontal force here. The only forces other than friction are vertical. They are mg and n. So why at all the static force of friction comes into play? If there is no external force in the horizontal direction, our system should not have a tendency to slip horizontally, and therefore how do we explain the appearance of the static force of friction? Now this is a problem in the inertial frame of reference to find out the reason behind the appearance of the static force of friction. Well, we resolve it. We resolve it in the inertial frame of reference. We say that it is due to the kinematical constraint. And what is kinematical constraint? Well, the kinematical constraint here is the acceleration, kinematical constraint. is the reason for the appearance of the external friction into play. This kinematical constant comes due to the acceleration of center of mass. The center of mass has twofold acceleration here, AT and AR. Each of this acceleration has a horizontal component. So it is kinematically constrained to have a horizontal acceleration, and any horizontal acceleration needs an horizontal external force to provide that horizontal acceleration. So there must be horizontal external force come into play due to this kinematical constraint of horizontal acceleration of center of mass. This is how we explain the appearance of the horizontal friction. Now, this same discussion, if we change the reference frame, becomes very easy to understand and very easy to explain, very easy to work out also. Suppose we take our reference frame, instead of inertial, I take a reference frame fixed to the center of mass of the rod. That is, this is the rod at any instant t, and the center of mass of the rod I take my reference frame. This is a non-inertial reference frame. The center of mass has twofold acceleration, AT and AR. So now in my system, besides the real forces, well, the real forces are mg, the normal reaction, and static force of friction. Besides these real forces comes into play the pseudo forces, and pseudo force is mass into acceleration of the frame of reference, and therefore the two pseudo forces that comes into play, they are in opposite direction to the acceleration, of course, by definition of pseudo force. So one pseudo force is m into AT, and the other pseudo force is radially outward m into AR. Now we find there are various forces, and both of these pseudo forces has a horizontal component. Now we can immediately say that our system is experiencing an external horizontal force that gives it a tendency to slip. The horizontal component of the pseudo forces gives it a tendency to slip horizontally, and therefore the force of friction will come into play to oppose that tendency of slipping, and hence the force of friction comes into play, and that is must be horizontal because the floor is horizontal. There is no question about that. Now you can wonder, is this pseudo forces are real forces? Well, obviously, in inertial frame of reference, they don't have any existence. That is why they are called pseudo forces. But in the frame of reference of center of mass here, which is the non-inertial frame, these pseudo forces are very much real forces. If we want to draw the equation of motions, which follows from Newton's second law, that sum of all the external forces in a direction is equal to mass into acceleration in that direction, then we must take into account all the pseudo forces as our real forces. Let me give you a simple example why and how these pseudo forces are real forces in this frame. Imagine you are traveling on a vehicle. You are standing on the floor of the vehicle without any rod that you can support with while standing on the floor. And now suppose the vehicle suddenly takes a turn. As and when the vehicle takes a turn, you feel that someone is trying to throw you in the outward direction. That is, an external force, as if an external force acts on you in the radially downward direction. You really feel that. And you immediately try to hold some support to keep you stationary relative to vehicle. It is this force which we don't find from inertial frame. It is only observed in this non-inertial frame, in your frame, rotating frame of the vehicle. You are in the non-inertial frame, so you experience really this pseudo force trying to throw you out. This is what a pseudo force is. It is a real force in the non-inertial frame of reference. And that is how and why the friction comes into play here, that we can explain by invoking the non-inertial frame of reference. So, discussing the problem, while discussing any physics problem, it is very much essential to remember from which frame you are working out the problem. In a non-inertial frame of reference, some problem can be worked out very easily. So often, while discussing this type of problem, we may have to follow the non-inertial frame of reference. Thank you. I'll again come back to the discussion of this falling rod problem because there are some more interesting insight to be discussed. Thank you.